In this video, I will look at a question that relates angular acceleration to linear acceleration and also involves centripetal acceleration. First thing I've done is to draw a picture of the turntable. We know that there's a radius that we're dealing with of 8 centimeters. I actually don't like centimeters. I want to change that to meters. So first thing I'm going to do, instead of 8 centimeters, 0.08 meters. 33.3 RPM, revolutions per minute or rotations per minute. That's not an SI unit either. I want it radians per second. So I need to convert that. So 33.3 rotations per minute. I know that I can convert minutes to seconds. 1 minute per 60 seconds. We're getting closer. Now I need radians. I know that there are 2 pi radians in 1 revolution, or 1 rotation. So the rotations cancel out, the minutes cancel out, and I get, it's about 3.5 radians per second. So 33.3 RPM, .5 radians per second. It starts not moving, so I should put an omega naught is 0 radians per second, and then it takes 0.4 seconds to get from 0 to 3.5 radians per second. All right, so now what we're looking for is the acceleration of a point 8 centimeters away just after we turn it on, when it's running at full speed, and just before it reaches full speed. So when we just turn it on, so it started out, it wasn't moving, and then it's starting to accelerate. We assume uniform acceleration. So just like acceleration is change in velocity over change in time, angular acceleration is change in angular velocity over change in time. So that is omega final minus omega initial over t. So that's just 3.5 radians per second over 0.4 seconds, 8.75 radians per second squared. But we weren't asked for alpha. We were asked for A. And we know A tangential is R alpha. So 8.75 radians per second squared times 0.08 meters, 0.7. Radians go away when you multiply it by the meters, so meters per second squared. So this is the tangential acceleration. Since it's not moving initially, it has 0 speed, we're looking at just as we turn it on. That means there's actually no centripetal acceleration. So the tangential acceleration is the only acceleration it has. So A at the start is 0.7 meters per second squared. Tangential direction. So whatever point we are around here, it's in the tangential direction to that point. All right, so that's the first one. What about A when it's running at full speed? When it's running at full speed, it's not increasing in speed anymore. So that means this delta omega is constant when it's running at full speed. So if that's constant, it's not changing. So tangential acceleration is actually 0. Okay? So AT is 0 at full speed. But if it's spinning in a circle at a certain speed, we know there's centripetal. So the centripetal acceleration is Vt squared over r, or in this case, since we know omega, we can use r omega squared. So that's 0.08 meters times omega final, 3.5 radians per second squared. 0.98 meters, radians go away, per second squared. So that is A at full speed. Okay? So 0.98 radians per second squared in the centripetal direction toward the center. What about the third one? Just before it reaches full speed, it's basically moving at this omega that we used here, 3.5 radians per second squared. So it has a component, 0.98 radians per second squared, toward the center. It also has, it's still increasing, it's not quite there yet, and we're assuming constant acceleration. So it has 0.7 meters per second squared tangentially. So it's got 0.7 this way and 0.98 that way. Both of these are meters per second squared. So A would be equal to the square root of 0.7 squared plus 0.98 squared meters per second squared. That's the magnitude of it, and we'll know that it is pointing somewhere in between the radial direction and the tangential direction. It has to be pointing this way somewhere, but we won't calculate the actual angle of it.